So let's go for it. I think this is where we left off. Let's go with line. The distance of a line or the length of the line matters quite a bit, right? Let's see. And if you're pointing south, that is going south. If you're pointing north, it's going north. So direction matters. So the length of the line and the direction it goes matters. And I think we took notes on this one already, right?
Yeah.
Okay, so we're jamming with the next one.
Yeah.
We got this one.
Yeah.
That's right. That's when Matthias did his radio voice. Right here for vectors.
Oh, yeah.
Right? I remember that. And then we got to this one. Oh, yes, equality of vectors, right? Same direction, same length means they're the same. And then we have, and you can do it algebraically as well. So you can say V1 is equal to V2. And you have the algebra behind it here. And then you have the zero vector, right? It's not defining any direction. It gets you back to zero.
So if a vector doesn't have magnitude or direction, does it exist?
Is it a vector?
Because it just seems like if it doesn't have anything, it doesn't, it's not there.
Right, yeah.
Is it just like 2 zeros? Is that why
Yeah. We do it for calculation purposes, literally. So when you add up all the forces together and you get zero, you know you've got all the forces. Okay. It was almost a theoretical question. Like, you know, if there's more space between electrons and protons, and is there really something there? I don't know. Something like that. It didn't work out well. Right? No, you guys are not in particle physics too much, huh? Right? Right. So the saying goes, because you have an atom, but inside the atom, 90% of it is space, right? It's the distance between the protons and neutrons and the electrons themselves, right? So 99% of it is space. You got these little funky things floating around at the bottom. So is the chair really there? Okay, never mind. That didn't go anywhere.
If we define there are like we can experience ourselves, then yeah, like it doesn't matter how small you know, if you can touch the thing, then it is there. Then are you really?
I can see why Descartes really liked it.
Okay, let's go with adding, subtracting of vectors. So.
Oh, this is the part that was in the lecture that did make sense.
Okay, good.
Well, actually,
Okay.
I do have one question.
Idiot!
Grant? What was that?
So, can you just like every day? Can you just like rearrange vectors to just make it work?
Absolutely. Any which way you want. So you can add them up any which way, just like addition is 3 plus 4, 4 plus 3 is the same thing. So vectors, you can do u plus v. That is absolutely the same as v plus u. And notice that little line right over here. There's your v vector, there's your u vector, and it gets you the same resultant vector. So therefore we know they're still additionally, they're still the same thing.
Yeah, so couldn't you just rearrange the vectors to make any length of line in between? Like if you just write them like this, and then the line is only that short, like why is it?
You can change where they are in space, but you can't change the direction.
Yeah, you're right.
Yeah, but her question is, we add them up sometimes, and most of the time we add them up or subtract them because we're trying to get to a resultant vector is the addition or subtraction of them. Because whenever you combine forces, we'll see on the next slide, whenever you combine forces, you do have to add up all the sum of all the forces you have. And so you do point them head to tail, head to tail, head to tail until it's all done. Okay, we're good there with that one. The slide that made sense. The only slide that made sense. Okay, so this is a good one here. Okay, sounds good. Keep on going. 2 slides that made sense. Thank you.
The slide made sense. It was just us not understanding.
No, we're good. So all these forces are acting on the car, right? And so if you were to add up all the forces, if it's stationary, if the car is stationary, if you were to add up all the forces, you should get a 0 vector on your hands, okay? Or, even better yet, if you add up all the forces head to tail, head to tail, head to tail, they should start and eventually end in the same spot. Good? Then you know, like, okay, I've accounted for all the forces that are here. It's so interesting. Learning about how they did computer animations for weather, it's getting better, right? But it's this whole concept of, oh, we didn't add this force into it. Oh, we didn't add this. And then eventually, after 4 or 5 years, then it's like, okay, I think we're getting close to how weather's simulated. And then now you can start predicting. I don't know, they still do an okay job predicting. Okay, so with the car, are we good? If we were to add up all these forces, the weight, the reaction force, the driving force, friction, air resistance, eventually we start one spot and we end at the origin, literally. Okay, there's that, and then of course the incline. Okay, so let's add and subtract these guys here real quick here as a visual. There it is, U is here, V is here. I'm not sure why I did it twice. The resulting vector is there. Makes sense? I think I had these move, that's why. There you go, yeah. I had these little guys move eventually, and then I had to redo it. Subtraction goes the other way. You just point the arrow goes the other way than it originally did. So if you were to subtract these, it should look like something else like that. We good? The resultant vector looks a lot different, right? Okay.
Yeah, here's where it goes.
This is where it went. Okay. So Hayden, I didn't know you own a boat, but you're crossing a river that runs exactly south. Okay. Rivers generally tend to do that. Kind of, sort of. Well, depends. Yeah, depends on the gravity. The boat is pointed due east and is moving through the water at 10 miles per hour. That's great. If the current of the river is a constant 15 miles per hour, the actual course is different. So Hayden's on. Let's see, find the actual course of the boat. Hayden is on through the water. I don't care too much about the two significant digits as long as we're kind of there. So if I was going to draw this, so north, south, east, west, there's my little directional map here, and I got my little river flowing right here from one side to the other, and I got my little water. I added no water. And then, see, if she's going east, that means she should have started here. And then she's going that way. And so as I draw my little arrow, I'm thinking in my head, that's about my 10. Whatever my 10 miles an hour, that's going to be my 10 miles an hour. So however long your line is, keep that. So if we draw a 20, we're going to double that somehow. We good? But we're drawing a 5, and we're drawing a 5 due south. If you want to put little numbers there, that's cool. Put 10 or 10 miles per hour, so you have it. The current of the river is a 5 miles per hour due south. So I got that one, and that one should be about half what you just drew for the first one. Cool. 5 miles per hour, that's done. And kind of interesting. These ones you have right triangles, right? You can tell, right? Because the boat's going to go this way, and it's crossing horizontally across the river, obviously going to have a right triangle. What gets pretty cool is when you get into the ocean and you have all these different currents that are actually happening, then you need a little bit more sophisticated trigonometry, which was, all these fun stories here, which was invented by Mr. Bowditch. Anybody know about Mr. Bowditch?
Oh, yeah, we read it.
Yeah.
I remember, yep.
Okay, yes,
Oh, yeah.
When was that? How long ago?
Yeah, something like that. Yeah.
Oh,
Remember,
wow.
everyone that he loved died, so.
Okay. Yeah, let's see his.
Fun.
I remember the cover, he had like the little.
Yeah, I only remember I only remember like a large chunk of blue on the cover.
Yeah.
That's the one. Yep, that's the one. So yeah, sold by his dad because dad was a gambler, right? And sold to the shipman.
I remember, yeah.
And he can only visit his sister, what, once a month or something like that? And got interested in the person's library, so he started reading and reading and reading. I went to Midway in, is it San Diego? Right by San Diego? Where's Midway? The ship. Yeah, I think right outside of San Diego. So when you go there, we had the tour, went up to the top, and you had these instruments, and you actually had Mr. Bowditch's navigational chart still there. Like they were actually like, I know that. That's so cool. So we had a little discussion with the curator of the place, or the person that's in. That's awesome. But anyways, his stuff is still used, even though we have gone digital quite a bit of GPS as the backup plan. Like I was saying, yep, they're still there as the backup plan. Anyways, let's go with it here. So what's the actual true course? It's the resultant vector. It has to be that one right there. So now the question is, what is the bearing of the boat that Hayden is on? All right. Let's do some math. With magnitude first. So Pythagorean theorem still works, is that right? If I have a 10 and a 5, I can get the magnitude of the
When I saw this at first, I thought it was literally like u plus v right there, so I was like 10 plus 5 is 15, and that doesn't make sense at all because this is so much bigger than this line.
It'd be a straight line, yeah, because you're adding 10 plus 5. Okay, I'm going to put my little 2's in here. Squared, squared, all yours to find C. Right.
11.1.
Yep, I went for the exact answer, and then I'm going to give the approximation as well here. So
1803.
Okay. 18. So 11.2 is fine. 11.2 would be okay. Since we have 10 miles per hour, 5 miles per hour, notice the significant digits there. So you could even do just 11. That'd be fine. All right, and then of course the angle measurement here. So we have this little guy here, and we're trying to figure out that angle there. So the question is, which trig function you want to use? Tangent is good by me. Yep. Opposite side over adjacent. There it is. You could have used sine or cosine as long as you use the 5 root 5, right? Because that would still be an exact answer. You would not want to use 11. So that's an approximation here. So tangent inverse on a little calculator here. Anybody give me that? 6.6 is just fine by me. Awesome. Okay, so we have that little angle. Remember, our bearings are always either from north and south, right? It doesn't, we're always going to go from there. So I think what I want is I actually want this angle right here eventually. You make this into a north, south, east, west. That's what I want right there. That's going to be 90 minus whatever angle I have. So 90 minus 26.6. Let's get that. And then let's see. Right, and I could have made it to you to give me into minutes, degrees, minutes, and seconds, right? There's another option. So I got a 4 there, I got a 3 there, and a 6. Are we good? 63.4 degrees, roughly. And I think I'm good. That's going to be 11.2 or 11. That's fine, either one of those. And the final answer. So need extra time there. All right. Are we okay with south? 63.4 degrees east at 11.2 miles per hour or 11 miles per hour? That's kind of cool. Okay, everybody good with that one? Any questions on that one? Okay, jam. Let's go with the next one here. Grant, I never knew this, but he is a human cannonball sometimes.
I do. Sure.
He shot with an initial velocity of 67 miles per hour and an angle of 60 degrees from the horizontal. So now we want to find the magnitudes of the horizontal and the vertical components. Ooh, a little different here. So notice this is not direction anymore because granted it's not going to be shot 3,000 miles, so that you have to figure out the direction upon the Earth, right? So this is just inside a tent, going from one side to another. A little circus here. So there's Grant, whee, out of here. And then we have a little angle measurement here. So then a lot of times with vectors, you do have two components to them. You got the horizontal and the vertical. And when you put those together, you have what you need as the full vector. Sometimes you break them down because you only want a piece of it. You want to know how fast they're traveling sideways. You want to know how fast they're rising up in the air if they're going to space, right? You don't care about their trajectory horizontally. So when you fire a rocket, we're concerned as how much altitude they're gaining right away. Right? If they're turning, obviously we want the route to be good, right? But if people sitting in the space center, one's just looking out for altitude, make sure they're at altitude. So that's just a vertical vector. All right, if that's the case, you guys talk to me. If I know this right here, what would give me this little x value right here? Give you the answer. Which trig function will give me that? I think it's cosine. Is that cosine? This is the 60 degrees. This is adjacent side, and that's the hypotenuse at this point. If you drop a little altitude down, right, and make a little triangle. That's cool. Vertical component would be, yeah, what would be the vertical component? What would give me the y-axis? So if I were to drop this down like this, right, boom, this is cosine of 60 degrees easily, or cosine theta would give me this little component. What would give me this component?
Then you could,
Like 30 degrees.
yeah.
Don't write this down. Okay, go ahead.
Then you could do, yeah, you could do cosine.
Yeah, you can do cosine again right here. Boom, 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 boom. If you found the 30. How about this? Interestingly enough, if you're here and you take this across, isn't this piece here the same as this piece here? Will those be the same lengths, at least vertically? Oh, that is so cool. So that side there. So hold on. What would give me this side here? Which trig function would give me the opposite side related to hypotenuse? It's sine. That's awesome. And then I don't need to get the complementary angle. I could still use this angle. We good? Awesome. Okay. As long as PowerPoint's keeping up with us. There it is. So that is so cool. So we have a horizontal component called Vx. And all it is a magnitude of the vector itself multiplied by cosine. No. We'll wait for you. Thank you. So I forgot to finish up the problem. We all forgot about Grant. At least I forgot about Grant. So I'm going to go like this. I'm going to go 60 degrees. And this is 67 miles per hour. Is that right? So let's go with it. What is the horizontal component? So V of x, the horizontal component would just be 67, or absolute value of 67, or the magnitude. Sorry, I'm saying it wrong. It's the magnitude of my V vector, right? Times cosine of 60 degrees. Anybody with an answer there to, nearest whole number.
What does it say?
Oh, of course, my chicken scratch here. Thank you. It's cosine of 60 degrees. That's right. Got to get calculators out now. All right. Make sure you're in degree mode. Yeah, can I change up a little bit things right quick? Let me drop this absolute value. It's not absolute value. It's just the magnitude of the vector, which is 67. Oh, cool. Okay, 34. We'll go with 34 miles per hour. So he's going horizontally across 34 miles an hour. Vertically, 67 times sine of 60 degrees, all there. Okay, awesome. Thank you so much. 58 miles per hour. Da, 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 da. Done. So we figure out the components.
So why are there like the absolute value signs like around the last equation?
Sure. This part is just because it's, so it's not absolute value, it's magnitude of your vector. So remember, we're using the same symbol for two different meanings.
Okay.
And so that is not absolute value, it is magnitude of vector. Okay. Sorry, go for it.
So is the actual vector just like the arrow itself, and then the 67 is the magnitude?
Yes, correct.
Okay.
So vector relies on length, right, and direction. That's the vector. So you technically can only, well, you can draw a vector. That's easy, right, because we do graphs. Or you could tell me, hey, the vector is 67, and this one would be 60 degrees elevation, right? That's the way you would say it. The way to do it is by bearings, right? It's 63.4 degrees or south 63 degrees east with this many miles an hour. Does that help with that? Okay. All right, we good? Another one? Sorry, see about a couple of people still writing it out. Go for it. All right, if you're going to go backwards, that's what this little guy says on the bottom right here. Is this if you do have the component vectors and you're trying to find the vector of the both of them combined together, that's how you do it. So you do Pythagorean theorem on the magnitudes themselves, which we did when Hayden was crossing the river. Right, that's exactly what we did. And we just took a square root. Okay, are we good now, guys? Good. All right, all yours here, beginning to end. Oh, you know, this is my, yep, cat shoots an arrow. Good, I'm not an English teacher. Into the air, so it's the horizontal velocity is 30 feet per second. Its vertical velocity is 20 feet per second. Can you find the velocity of the arrow itself? So now we're putting things together. Good catch, good catch. Normally let's see if I'm kind of thinking any examples or any applications of it. Normally we look at the components individually. So if we're satellite image on a convoy, right? You don't care if they're going up a hill or down a hill. You care about their horizontal trajectory, where they're at, how fast they're going to get a certain location, right? If you're launching a rocket, obviously, yes, then altitude is a lot more important than the distance horizontally. So all these different pieces here. Okay, so I got this right here. Arrow is shot. I know this piece to be 30 feet per second. I know this piece to be 20 feet per second. And so the resultant vector would just be that little formula on the bottom that we did. We can actually, I'm thinking we can even erase the, I would write it like this here. You're just squaring them, that's all. All right, from the velocity. All right, velocity is also how fast you're going, right? Cool. Are we good there? Anybody got an answer yet? It's 400. I can probably do this here. 400 plus 900. Is that 1300? Square root of 1300.
36.
Exactly?
0.0555.
Okay. I'm going to go with just 36 then. 0.0555 would be 36. So 36 feet per second. All right, we're good.
And that's the arrow, like, that is
So this is,
diagonal.
uh-huh.
Yes.
We do
So
correspond.
much sense.
Awesome. When you watch a video that doesn't make sense, and then when you watch a video that does make sense, total contrast. Oh, interestingly enough, my daughter is taking a, it's called AutoCAD, engineering major at Cuesta. So they're doing AutoCAD. So you're looking at something from all the different angles. And absolutely, she's computing this stuff all the time. Because we make a model of something, let's say a hinge on a door, right? You got to see it from all these different places. Or if you're putting a sleeve for a bolt or something like that. So that was kind of cool. Like, oh yeah, you're just doing it's stationary vectors, but it's still technically vectors. Okay, I think I could do it this way here. Let's see. I'm going to go here. Yeah, you can still do that here. So next piece here, I got the 30 and the 20, is that right? And we're gonna have to figure out this little angle right here. I gave you the trig function already, that's no fun. So notice what I did is I've changed it instead of the vertical on being on this side, right? I switched it over, now I got myself a little triangle. So technically, all these things have formed a triangle because I can go tail to head, tail to head, tail to head backwards, right? All right, 20 over 30. Same thing would have happened if you put your calculator, put in 2 or a 3. That's fine, right? Because the ratio between the two, right? And give me angle. Anybody? Perfecto. Okay, so here's what I got. The arrow is shot at 36 feet per second with an angle of elevation of 33.7 degrees. All right, notice we're not using the north, south, east, west, right? Because we're just shooting it too small of a distance to even do that. Let's copy it down. Let me see how many slides I still have left. I think we'll do that. Boom, force. So here's another little thing here. here's what we're talking about. Remember the car? Initially we said there's a driving force, there's gravitational force, there's friction. So all these different forces here. So if an object is stationary, the bottom little paragraph is important here. Well, don't need to copy all this down. I'll let you guys read it. How about that? Let you guys read it. Why should I read it? I typed it. I read it. So, so gravity is one single force. You want to weigh 6 times less, just go to the moon. Totally cool diet program.
Great way to lose weight.
So, good there. So, that is a force. It forces our weight. The direction is gravity, so therefore we get weight. Let's see, another thing is if the object is stationary, the sum of the forces there is my zero vector right there. There's my, I should be able to connect them and they come back to the same thing. So let's jam. That's saying the same thing. So let's go with it here. I didn't want to put any of your names on here because then you guys are not 5 years old. It would have been a fun little thing. Physically. All right, Danny's 5 years old, weighs 50 pounds. He is sitting on a swing, and his sister Stacy pulls him on the swing back horizontally through an angle of 30 degrees, and then he stops. So Danny now is stationary before big sister lets him go. So we've got to do this here. Find a tension on the ropes of the swing, and the magnitude of force exerted by Stacy. That's cool. And so we have 2 Dannys on the picture though, right? Danny's sitting there by himself and then Danny scooted over. All right, let's go with it here. Let's keep these little guys right here. So T is the tension on the rope. H, I'm not sure why they didn't do S, but that's fine. That's Stacy pulling it out. Oh, horizontal, I guess, yeah. And then the weight of Danny. Good there. Let's see if we can. So here's what I'm looking at right here, right? There's all little pieces there. I'm going to go just a little bit faster just because we need to finish up in 10 minutes here. So we go this way. Okay, here's the fun part. Can you rearrange these head to tail, head to tail, head to tail so they start at the same spot at the end? And no, I know there's 2 different ways. I almost want to say there's 4 different ways to do it, but here's, so we keep all the same here. We're good there. I'm going to do the tension first. And then the horizontal. And then when I bring this down, it becomes, wait, I want to say there's, I'm thinking of, there's 6 different ways to do this. So your calculator will look 6 different ways. You should get a right triangle somehow. And there's my 30. If you're having difficulty in the homework writing it, then what you do is keep the arrows where they should be. So notice the horizontal, the arrow would be right here. And then when you tack on the tension on the rope, then the arrow comes over here. And then the weight gets you back down to here. So if you want to stick in the arrows kind of give you a little sense of direction. Okay, so we need T, I believe, and we need H. And W, we know, W is 50. All right, gonna go just a little bit faster here. Right triangle, you should do it somewhere, sometime there. So let me redraw it real quick here. I got this, and I think I'm good to go. Magnitude of W is 50. And if that's the case, tell me if you agree or disagree. Kind of look at magnitudes themselves. I got cosine from the 30. Cosine is going to be the adjacent side over the hypotenuse. We good? So I need to somehow correlate W with something. And I can plug in the 50 for the W. Voila. And how about multiply both sides by the, I don't know what that is. Tell me if you guys are okay with that right there. Not with this little funny thing right here. That's, I don't know what that is. So multiply both sides with the magnitude of t divided by cosine 30 and give me 50 divided by cosine 30. 7.73, that's cool, yep. And then what we always do is we're going to put it into pounds. Pounds is what we have it in. All right, all yours for the next one.
Wait, so why are we putting it in the pound?
Sure, because that's the way we normally use weight and tension, and because Danny's in pounds as well. So the force that Danny's applying is in pounds, so the pounds also have to add up to zero. So the force that we're dealing with. Some other, because I'm thinking pounds usually is the force. Let me see.
So why is it more than what it is?
That is so interesting. That's cool. Georgia has a question. How come the tension on the rope is actually more? Anyways, kind of two different answers to it. First of all, because we still have to figure out the horizontal piece here. But because, we'll see on the next slide when we do work. Whenever you bring an angle into something, you actually have to exert more energy or more force than the straight angle. So moving a piano, which I had to do recently, if you move it straight, all the force is exerting this way, right? But if I'm coming to the piano at an angle, in order to still move it horizontally, I actually would have to give more strength to move it. If that makes sense. Because only a part of me now is moving that horizontally.
So it's like Stacy's pulling on it is adding the weight?
Stacy's pulling on it, and each time Stacy goes more, there has to be more tension on the rope in order to keep him stable. Yeah, All right. Now, if you guys agree here, this is tangent of 30 degrees now is I want the relationship between H and W, which is opposite over hypotenuse. I'm going to use tangent. This one's a better one because because last time we had 50 on top, so you had to do two full pieces here. This time I'm looking at 50 on the bottom. So I just multiply both sides by 50. I get what I want. Anybody with that calculation? 20.9, perfect.
Wait, why would it be tangent? Because wouldn't it be, are we doing the 30?
No, we're doing it 30.
So wouldn't it be opposite over hypotenuse?
No, because T, we had to calculate T over here. What we do W. So we're making everything in reference to W. Cool. Are we good there? All right, with a little bit more to go. So there it is. I think we got it. Tension on the rope is 57.7 pounds, and Stacy exerting 28.9 pounds on that. Okay, one last thing with 3.5 minutes to go. Boom, is work. How much work is performed? So yes, the moving that piano. If I move it, there's my exertion of force on it, right? Let's say I move it 100 feet. I have to include that little distance of how much, right? Because if I only moved it 50 feet, I didn't exert that much work, right? I only exerted half the work. So this little d right here, d just means distance. We multiply the force times cosine to give you the horizontal distance applied. And then we multiply by the g value to how long you've done it. If you're going to write down a formula, this would be it right here. So W work is equal to magnitude of F cosine theta times D. Cool. All right. Mr. G. Mr. G is pulling 2 elementary school students in a wagon, force of 25 pounds on the handle. So now we know how much force is applied. 30 degrees is the handle. How much work is done by Mr. G if he pulls it 350 feet? So there's what we were talking about earlier, Georgia. Right? If he was pulling exactly horizontally, then that would have matched. If he has an angle there, he has to exert more force. If he's totally vertically, then he's not exerting any force horizontally. He can't even move it horizontally anymore. All right, with a minute and a half left, let's go with it here. So here's what I got. I got 25 going up. Here's my little right triangle. I have my 30. And I'm not putting my 350 feet in yet. I just need to figure out what this is. Can I do it a different way here? Let me do it by formula because I did it the long way here on this guy. There's that. So by formula itself, we are technically trying to get over here, but we do it by 25 because that's already the magnitude. Cosine of 30 degrees multiplied by 350 feet. So if you're just going to use the formula for work only, that would be easier. Anybody got that? And in physics, when you guys start doing physics, you guys will find out work. There's a whole bunch of different formulas for work. 600 something something? Oh no. Or 7,000 something something.
Yeah.
Thank you. 7,000? 78? Okay. All right, and we're going to call it foot dash pounds. So it's the pounds is already the weight distribution, right, of things, and then we carried it so much feet. So that's a unit value. Okay, 2.5 made sense now. So much more, right? Yes. Okay, so Wednesday we come back. We do any homework questions. Please bring in your homework questions you guys have Wednesday. And then we set up a little test for Friday.